This is the video for Chapter 4, Part 2. We're going to look at the properties of the linear correlation coefficient. This is this R value that we are going to find using StatCrunch. And the linear correlation coefficient is always going to be between -1 and 1. That's it. Of course, it could be -1 or it could be +1, but somewhere within that range of values, that's where our correlation coefficient will be. When it is +1, then there's a perfect positive linear relation that exists between the two variables. It would look like this. It would have a line, a straight line of dots. So all of the points, all of the data would be able to make a straight line. And as you can see, this positive slope or positive relationship, that as x increases, so does the y value. Now, for the third property, if r is -1, then a perfect negative linear relation exists between the two variables. And that would look like this. And that negative relationship means that as x increases, then our y value actually decreases. All right, properties 4 and 5 are just kind of go off of what we had for 2 and 3. The closer r is to +1, the stronger the evidence is of a positive association between the two variables. And so if we see this here, this isn't a perfect line, but they're very tightly around this line. And so this might be like an R value of maybe 0.9. Similarly, the closer our R value is to -1, we've got stronger evidence saying that there's a negative association between the two variables. And so there's an example of a negative relationship. And again, in this case, this one's not quite as strong, but maybe R is 0.7. I'm just kind of taking a guess of what it might be. And if R is close to 0, then little or no evidence exists of a linear relationship between the two variables. We have to be very careful, though. This word linear is important. So it doesn't imply no relation, just no linear relation. And I've got a couple of examples here in a minute that will show you when we might have something that's just not a linear relationship, but it still has some sort of relation. All right, and then our last two properties are here. So number 7, the linear correlation coefficient is a unitless measure of association. So the unit of measure for x and y play no role in the interpretation of R. Now, the units that we have for x and y will matter when it comes to slope and the y-intercept, but as far as R is concerned, there are no units involved. And then number 8, the correlation coefficient is not resistant. So remember, a resistant measure does not change if there happens to be an outlier, but a non-resistant measure is affected by outliers. So the correlation coefficient can definitely be changed based on an observation that is different from the overall pattern. And the interesting thing is you can have a value that's not an outlier for the x's or an outlier for the y's, but together it's an outlier for the pair. And I'll show you that when we go to StatCrunch. All right, so again, here's our data set from the clubhead speed versus the distance. Of course, we saw our scatter plot here. I'm gonna just kind of move this to the side. We're going to look at this in a minute and see the difference that an outlier can make. But first, I want to show you how to find the linear correlation coefficient, that R value. To do that, we're going to go to the Stat menu, down to Regression, and we'll always use simple linear. So like I said, there are many different possible values that we could have, or different relationships we can have, but we're only going to look at the linear relationship. We already talked about, we are going to talk about club head as being the x variable, distance being the y variable. Now, right now, there's nothing else that we need to worry with in here. There is something that we could use in the future, prediction of a y, but we'll talk about that in a few more further along in the video. So when I click compute, I'm going to get a lot of information, and I posted this in Momentum. We don't need to worry about any of this stuff down here. So all of this is just extra. The only thing right now that we care about is this one value right here. All right, so finding the linear correlation coefficient, finding that R value isn't really enough. We also need to be able to tell, based on the sample size, whether or not that the correlation is strong enough. And so these are our cutoffs, these are our critical values. And as long as our R value is greater than this value in the table, then we should be good. And a lot of times we'll say that the absolute value of R needs to be greater than this value. Absolute value, because it doesn't matter if it's a positive or negative relationship. The number portion of the correlation coefficient needs to be bigger than this number here. And of course, you'll be able to use this on your homework, your quiz, and your test. All right, so we've seen a couple of these already, but here are some examples of scatter diagrams or scatter plots. Of course, we already saw this one. We said it was an R of 1. So down here is an R of -1. We also saw this one, and I said it was probably somewhere close to 0.9. This next one underneath it might be a little bit tighter. So we might say maybe, 9.3. I don't know, I'm kind of making things up. If we move over, we already saw this one, and I think I said it was maybe a 0.7 or 0.75. This one, excuse me, I've messed up. This should be negative and negative. Very important that those negatives are there. In fact, I'm going to rewrite them so that the negatives and the decimals are not on top of each other. So this should be negative 0.9293, and this one should be negative 0.7. And then this, right above this graph, we might say that that is, I don't know, it'd probably be close to 0.7 as well, but positive. Now our bottom row has two graphs where the R values would both be really close to 0, likely. However, to say that there's no relation between these might make sense for this first graph on the left, but does not make sense here. So this one definitely has a relationship, it's just non-linear. So that's why we say there's no linear relation between those two variables. That's very important because it's not always going to be just a scatter shot like the graph on the left.